Okay, let's start with the example number 6 for drawing the root locus. Again, here GC is provided as KP and GP is provided as 2 divided by S times S plus 1 times S squared plus 4S plus 13. And our aim is to draw the root locus for the system, both for negative values of KP and for positive positive values of KP. But before going forward, let's rewrite our problem as 1 plus rho times ns divided by ds. And according to the values that we have for GC and GP, we can write 1 plus KP times 2 divided by S times S plus 1 times S squared plus 4S plus 13 equal to 0. And accordingly we can write 1 plus rho times 1 divided by the same terms, S squared plus 4S plus 13 equal to 0. So we have rho equal to 2 times KP in this case. We have no 0 and we have 1, 2, and 4 poles. Okay? For the poles which are obtained from this equation, RSCS, so I call them S1 and 2. We can calculate them. We have minus 4 plus minus square root of 16 minus 4 times 13 divided by 2. And if you calculate them, you will get two answers. Minus 2 minus 3j and minus 2 plus 3j. Okay, and accordingly we can rewrite the denominator s times s plus 1 times s squared plus 4s plus 13 can be rewritten as s times s plus 1 times s plus 2 plus 3j times s plus 2 minus 3j. So again we will draw the root locus both for negative values of KP and L and for positive values of KP in these graphs. P. We have 4 poles for the system. N is equal to 4. M is equal to 0 because we don't have any 0, as you can see the equation here. Ns is equal to 1, so no zeros, and we have 4 poles here. And accordingly n minus m, which is equal to 4, means that we will have 4 asymptotes. And n equal 4 means that 4 branches for PL and 4 branches for NL we will have. So first of all, let's determine the location of the open loop poles and zeros in our root locus. No 0, and we have 1 pole right at the origin, open loop pole, 1 pole at minus 1, and another pole at minus 2 plus minus 3j. Minus 3j. And same here, 1 pole at origin, 1 pole at minus 1, and two poles at -2 plus minus 3j. Now we need to determine the behavior of the asymptotes. If you remember, we can calculate xa as the sum of zi's minus sum of pi's divided by n minus n. In this case we don't have any zero, so we will have 0 minus sum of poles divided by n minus n, which is 4 in this case. For the poles we have 1 at 0 plus 1 at -1, so it will appear as 1 here. Plus 2 poles we have at -2 minus 3j and -2 plus 3j. And after simplifying, we will get x a equal to -5/4, which is valid both for negative locus and for positive locus. In order to obtain the angle of the asymptotes with the real axis, we have r times kCa, in which in this case r is equal to 4, so we have 4 times kCa equal to 2h plus 1 times pi, where h is equal to 0, 1, 2, 3 for positive locus, and 2h pi for h equal to 0, 1, 2, 3 for negative locus. So if we put the values for h and divide everything by 4, we will have kCa equal to pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. This is for positive locus, for PL. And for negative locus, we will have 0, pi over 2, pi, and 3 pi over 2. This is for negative locus. Now we can go back to our root locuses and draw the asymptotes. Remember that for both cases xa is equal to -5/4. -5/4 is -1.25, which is somewhere here. In the case of positive locus, we have the angles for the asymptotes equal to 5/4, 3 pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. So from here we will have one asymptote with the angle of pi over 4, the other one 3 pi over 4, 5 pi over 4, and 7 pi over 4. In the case of negative locus, the angles are equal to 0, pi over 2, pi, and 3 pi over 2. So here we will have these asymptotes. Okay. Now let's see what are the sections of the real axis which belong to our root locus on the real axis. For positive locus, again, we need to have an odd number of poles and zeros on the right hand side. And looking at here, at the position of the poles, we can say that the region between -1 and 0 belongs to the positive locus. So this is the only region that we have. And in the case of negative locus, the region from 0 to plus infinity and from minus infinity to minus 1 belong to our root locus. In the case of positive locus, it's from minus 1 to 0. And for negative locus, we have from minus infinity to minus 1 and from 0 to plus infinity. So going back to our root locuses, I will draw them using this red color. So our branches will start from the open loop poles, and since there is no zero in this system, all of them will go towards the asymptotes that we have. We have 4 asymptotes in each case. Looking at the positive locus, we can see that the poles here at the branches starting from the origin and from minus 1, they will go towards each other, and at some point they will depart the real axis and they will go towards the asymptotes. In the case of negative locus, the pole at the origin will go towards plus infinity on the real axis, and most likely the pole at minus 1 will go towards minus infinity on the real axis, and the other complex poles will go towards the asymptotes. However, let's find out what are the break-in points. Yeah? In order to obtain the break-in points, we need to solve m prime times d minus t prime times n equal to 0. N is equal to 1, so m prime is equal to 0. We know the expression for d, ds is equal to s times s plus 1 times s2 plus 4s plus 13. Just to confirm, s times s plus 1 times s2 plus 4s plus 13. Okay, and then we can just rewrite it in order to be able to derive it easily. So we just write s3 plus s4. It will become s4 in this case. We will have s4 plus 5s3 plus 17 s2 plus 13s. And by deriving it, we will have d prime equal to 4s3 plus 15s2 plus 34s plus 13. And then putting these values in the equation, since m prime is 0, we will have, and n is equal to 1, we will have minus d prime s equal to 0. Or accordingly d prime s equal to 0. So we need to solve this equation to see what will be the values for s which satisfy this equation, yeah, d prime equal to 0. For s3 plus 15, s2 plus 34s plus 13 equal to 0. Here I give you only the solution. There is only one available solution at s equal to minus 0.4 6, 7. You can try to see how you can solve this equation, yeah? But here I just provide you the solution. So we have only one break in point with the value equal to minus 0.46 almost. And looking at the root locuses that we have, we can see that it belongs to our positive locus because it's here. It is somewhere around here, I would say. What else do we need to calculate? We need to determine what is the departure angle for the poles. Yeah? So let's do it right now. We need to determine alpha departure. So we know that Q alpha departure is equal to sum of phi I minus sum of theta I plus 2h plus 1 times pi for positive locus, and sum of phi I minus sum of theta I plus 2h pi for negative locus. In this case, Q is equal to 1 because we have only one pole at each position. However, we need to determine the angle of departure for each one of the complex poles. Yeah. So let's do it for the pole at P1, which is at minus 2 plus 3j. We need to obtain the, we don't have any zero, so we don't have any phi I, we just need to determine the value for theta i's. By redrawing the position of the poles and zeros that we have, so we have one pole here, another pole at minus 1, one pole here at minus 2 plus 3j, and another pole at minus 2 minus 3j. And this is our P1. So we want to obtain what are the values for each one of the poles, each one of the theta i's. So you should remember now how to do it. We just connect the corresponding pole to there, and we draw a horizontal line from there, and this will give us theta 1. Doing it for the other pole, we will have theta 2, and from the third one we will have theta 3. So obviously theta 3 is equal to pi over 2. Since Q is equal to 1, I just write alpha departure equal to phi I is 0, so we have minus, and we need to insert the value that we have for the thetas. So here we know that this side is equal to 3, and we have values for each one of these sides. Here is equal to 1, and here is equal to 2. So just by replacing the values that we have and using the trigonometric equations that you have, you can just simply obtain the values for the thetas. I just write the final result here. So for one of the theta we will have pi minus tangent inverse of 3 over 2. For the next one we will have pi minus inverse tangent of 3. And then for the last one, for theta 3, it's obviously pi over 2. So this is sum of theta i's, and then we have 2h plus 1 times pi, h is equal to 0, so plus pi, this will be for positive locus. In the case of negative locus, we have minus pi minus inverse tangent of 3 over 2 plus pi minus inverse tangent of 3 plus pi over 2 plus 0, and this is for negative locus. And then if we just put everything together, we will get alpha departure equal to a value close to minus 152 degrees for positive locus and around 38 degrees for negative locus. So this is the departure angle for this pole, for P1. We can use a similar approach in order to obtain the departure angle for the pole for pole P2, which is at -2, -3j. In this case, the departure angle can be obtained, as I only again write the final answers. You can just verify it. For positive locus we will have 152 degrees, and for negative locus we will have -38 degrees. Okay, so we start by considering P1 here. The departure angle for positive locus is -152. We have it here. So the departure angle for this pole at -2 plus 3j is equal to -152. So it will be somewhere around here. And then this branch will go towards this asymptote. And for the second pole, it is for P2, it's for positive locus, it's 152 positive value, and it will be somewhere, the angle will be something like this, and then it will go towards infinity along this asymptote. The other two branches coming from the pole at origin and the pole at -1 will meet each other at the breakaway point, and then they will start to go towards infinity along these asymptotes. Again, I just mentioned that these points here are important because those points show us what are the values at which for Kp from which afterwards our system will become unstable. Okay, we will check it later in a few minutes. Let's do the drawing for negative locus as well. In the case of negative locus, the angle of departure for P1 is equal to 38 degrees, and for P2 is equal to -38 degrees, and it makes sense because we need to have a symmetric root locus. Yeah. So if I draw the branches here we will have a branch departing this pole with the angle of 38 degrees going towards infinity, and here with the angle of -38 degrees going towards infinity, and this is all that we have. So again, here if you look at the graph for negative locus, we can obviously tell that for any value of negative Kp, for any negative value of Kp, our system is not stable, is unstable, because we have one unstable pole all the time. In the case of positive values of Kp, we can say that our system will be stable up to a given point. Yeah, afterwards the system will become unstable. Now let's see what is the question in the case of this example. So we need to find the values of Kp such that the closed loop system is bistable. So how to do that? If we want to have our system bistable, we can again use the Routh criteria. I will continue from here. And in order to use the Routh criteria, we need to form the characteristics equation. ds plus rho times n is equal to 0. In this case, ds is what we already have obtained in the simple format. ds is this term, s4 plus 5, s3 plus, so s4 plus 5, s3 plus 17, s2 plus 13s, if I'm not wrong, just let's double check, plus, yeah, plus rho times n, in which n is equal to 0. So this is our equation. For this system we can just form the Routh table for S4, S3, S2, S1, S0, and then put the values that we have. For S4 we will have 1, 17 rho, 5, 13 and 0. Now we need to fill out the whole Routh table, and I would like you to do it for me. So fill this part of the Routh table and then tell me what are the values of Kp for which the system, the closed loop system, is bistable. Yeah? Okay, so I'm waiting for your answers for this part of the question. And what's the next question? We need to find the value of Kp for which the step response will be undamped. When can we have the undamped behavior of the second order system, or the approximated second order system? So it happens whenever the poles of the system are on the imaginary axis. Yeah, it will happen right at this place. So if you find the value for Kp for which we have the stability, you will automatically find the value of Kp in which our system behaves like an undamped system. Yeah. So I'm sure that you will be able to find that value, and then you can tell me the answer for this question as well. Yeah? What is the value of Kp for which the step response will be undamped? So you can see that it is possible according to the graph, but you need to find out what will be the value. Alright, so that's all for this example as well. Again, don't forget to provide me the answers that you have for this part and for the next part as well regarding the undamped behavior. And don't forget to use MATLAB to draw the root locus for this example and send me the results by email.